Okay. Dang it.
Yeah, that's not, that must be, I don't know. I used to unless they try to add another section.
All right. So, dealing with Haar wavelets. So, what we're looking at is section 4.3. Haar decomposition and reconstruction. Okay. So the general process that I'm going to describe today is given some signal f of x, and just we're doing signals that have some sort of finite support. Well, let's face it, all signals anywhere have a finite duration. We wouldn't have a signal go on infinitely. And so just for simplicity, we'll assume that our original signal is defined on 0, 1. And the general workflow here is, and then I'll show you how these steps are carried out, is that we approximate using our Haar scaling function. Now, the Haar scaling function is piecewise constant. So basically, we're approximating f by a piecewise constant function. So f of x is approximated by fj of x, which will be a sum of coefficients. Well, I'll indicate the superscript j here to indicate that they are we're dealing with these scaling functions at refinement level j, if you will. So we'll have phi of 2 to the j x minus k. So the j indicates the how fine of detail we're going to get to. So for instance, if j is equal to 0, then we're just going to have one term that indicates that corresponds to, we're basically approximating f solely by a constant function on 0, 1. There's only one piece. If j equals 1, we have two pieces and so forth. So in other words, we're going to have 2 to the j total pieces with equal spacing. That would be 2 to the minus j, since we're working on 0, 1. All right. So, and the way we do that, this part is the easy part. Because the coefficients come from the values of f on the interval that I get by, if I set this equal to 0 and 1, because that's where the phi function is active. So we would have, if I set this equal to 0, I get, and solve for x, I would get 2 to the minus j times k, and then 2 to the minus j, k plus 1. So on that subinterval. Okay. Now, I say we're taking values of coefficients from the values of f on an interval. How you do that is a personal preference thing. You could take the average of f on an interval, or what if you've only and I'm going to, actually this phase has a name. We are sampling. So you might be sampling your signal at equally spaced points in time. and get your coefficients that way. So the point is, these coefficients come from the values of your signal at these, whatever sampling you do on these subintervals. So yeah, you might only be doing one sample and just use that. Because if you choose J to be large enough, so fine enough detail, small spacing, you'll get an accurate approximation. How accurate that depends on your needs. So again, a personal preference thing. Okay, but now that we have this, we need to. This is a good form to start with, but it's not helpful for signal processing tasks like compression or noise removal. We need to get it to a different form. So for that is the decomposition stage. Now, this function fj belongs to our space vj. That consists of linear combinations of Haar scaling functions at level j. There'll be these kind of functions here. But sort of decomposition will be into f0 plus w0 plus w1 and so forth, all the way down to wj minus 1, where f0 is in v0, so that's just a function that's constant on 0, 1. And then each of these w's are in the space of wi that are linear combinations of the Haar wavelet at that level. All right. So what we have here is these terms give us increasing levels of detail. As you go from left to right, you have finer spacing in X. High-frequency features come out down at this level, whereas here you get just low-frequency features. All right. This form is good for signal processing. So that is the next stage. Okay. Now, what that means depends on the task. And I'll just mention two tasks, ones I mentioned earlier. Compression. Now, each one of these W's are linear combinations of Haar wavelets at a certain scale. So each one of these will generally have multiple terms. Well, this could have as many as 1 term, 2, 4, 8, etc. So you have so it looks like I have just j terms, well, j plus 1 terms here, but really you have a whole lot more, because at a certain level you have linear combinations like these. Okay, so you have a bunch of terms to examine. So for compression, you remove the smallest terms. Okay. So if there are certain terms and I should emphasize here, at any level, from coarse scale features to fine scale features, if the coefficients are, in your judgment, negligibly small, toss them out, because that way you're able to represent all of f using fewer coefficients. Because once you have the coefficients, these AKJs at all the different levels here, and I'll show you how to get those later, you'll have everything. You don't need to values of f at individual x's. The coefficients will tell you everything. So if you can toss out certain coefficients, that's great, because then you can represent the same signal with decent accuracy with fewer numbers. Because as you'll see when I get to the next stage, reconstruction, if we need to go back to having a function of x, that's not hard to do. Okay. All Right, so that's one task, is compression. Just trying to represent the same signal or close to the same signal with less information, less storage. And then the other task is denoising. And that is where you remove highest frequency terms with the emphasis of any size. So even if you consider them not negligibly small, you still have to go. You have these high frequency oscillations that are contaminating your signal, introducing noise, static, whatever. Toss them out. Hopefully the audio signal, for instance, and maybe it'll be clearer after you remove them. So compression, it's about the size. Denoising, it's about the frequency. Now, what size or frequency threshold you set is, again, a personal preference thing. All right. And then once that is done, Reconstruction. So now that you've done something to your signal, hopefully enhanced it in some way, you want to go back to having a function of x. So right now you still have this kind of decomposition. This just changes the coefficients in decomposition, but after processing it still has this form. So now you want to put it back in original form, a linear combination like this, and I'm going to call these coefficients AKJ tilde, just to indicate that they've likely been modified. Well, surely some must have, or why do anything? Okay, so this is a nice signal processing framework using wavelet analysis. Okay, and the thing is, here I've shown how to do it with wavelets. Similar idea can be used for the Fourier Transform. It's just that Fourier Transform, we just only have one representation, because this is localized in physical space. This is localized in frequency and physical space both. With Fourier, you only get frequency space. You can do decompression and denoising with a Fourier Transform also, or DFT. It's just that you're not able to affect it's not easy to affect the signal locally in physical space by dropping certain terms. So that's one advantage that wavelets gives. And then reconstruction is like your inverse Fourier Transform. So there's a lot of commonality here. I just didn't explain it in this way, but here we have more control over how we mess with the signal. Because, like, what if you only want to, like, suppose your signal covers, like, maybe an audio signal that covers a whole minute, and maybe there's a 5-second part you want to work on and don't really care about the rest. You can do that with wavelets. You can't with Fourier Transform. Okay, so this is the overall framework, and there isn't really anything to this. It's just like sampling at various points. The only thing I really have to explain now is steps 2 and 4. How do we get the decomposition from this form here, and then how do you go back to that? And it turns out that the actual computation involved is actually not bad. Yeah. Any questions up to this point? Okay. Now, whoops. Let me make sure this is still recording. Okay. Now, so there's certain key equations that will really help us to do this. So for decomposition, so what we have is our building block for a decomposition algorithm are these two equations here. If I have my scaling function at 2x rather than x, that's equal to the average of scaling function at x and the wavelet at x. And if we do a little shift, so this amounts to a shift to the right of, whoops, that should be a 1 there. What was on my mind was 1/2, a shift of half a unit to the right. We get scaling function minus the wavelet. And the easiest way to see why this is true is actually through graphs. So I do phi of 2x. That is a function that is equal to 1 from 1 to 1/2. Or, sorry, from 0 to 1/2. And 0 otherwise. And then phi of 2x minus 1 is equal to 1 from 1/2 to 1. So in other words, you're taking the interval from 0 to 1, you're breaking it in 2 halves. So we go the first half, second half. And then if I also draw the scaling function wavelet as functions of x, okay, so suppose we take these and add them. These, the left halves, so I'll draw a dotted line here. The left halves will add together and give us 2, and then we divide by 2. The right halves cancel, so then we have nothing here. Similarly, if we subtract them, left halves cancel. By subtracting psi, the right halves add together to give us something here. If you really want to, you can just work this out algebraically, looking at points, points between 0 and 1/2 and points between 1/2 and 1. But I think that the picture is helpful here. Okay. Now, here we're working at the coarsest scale, like on 0 to 1, and then from 0 to 1/2, 1/2 to 1. But all we have to do is replace x with 2 to the j minus 1 x in these equations here, and we get something that works at any scale. So it expresses a scaling function at a certain scale and also shifted in terms of scaling function and the wavelets at the next coarsest scale up. So this is what we're going to use to, well, okay. Why this is helpful to us for decomposition? Because our function f, or fj, is originally represented this way, in terms of phi at 2 to the jx with shift. This tells us how to go up to the next coarser, so this is at the finest scale, Vj. But here this tells us how to express this in terms of scaling functions of wavelets at the next coarser scale. And we just keep going up and up and up and up. That is what helps us to get the pieces of f that are at all scales, from the coarsest to the finest. All right. So now what I can do is, let's see. Actually, yeah, I'm going to step through an example, f, and use these equations to show how you can decompose it how I want it in a form that's suitable for processing. And then I can show you the general output. All right, so I'll leave these equations up here so I can use them. Okay. All right. So for my example, we're going to work at j equal 2. So my f is a combination of scaling function at 4x with shifts. So I have 2, 4x minus 1 plus 5, 4x minus 2 minus 5, 4x minus 3. Okay. Now, and this belongs to V2. So I want to express this as a sum of functions in V0, W0, W1. Okay, like I described earlier. Okay, so the way I'm going to do this is I'm going to apply these formulas here. So starting with phi of 4x, that just means I use this with j equal to 2. So using this equation, I have 1/2 phi 2x plus psi of 2x. So that covers the first term. And then for the second term, phi of 4x minus 1, I can use the second equation, again with j equal 2. So I have phi of 2x minus psi of 2x. So that covers that term. Okay. Now, for these other terms, we have a little bit more work to do before we can apply these equations, because notice these always have a shift of either 0, so always just 2 to jx by itself, or with a minus 1, and we certainly don't have that here. So I'm going to rewrite this as 4 times x minus 1/2. And then this, I'll write as 4 times x minus a half minus 1. So now, if I again set j equal 2 in here, but I also replace x throughout with x minus a half, then I can go ahead and use these equations. So I'm going to have, for the third term, 1/2 phi of 2 times x minus a half plus psi of 2x minus a half. Okay. So that accounts for, the third term for plus. And then for the last term, I'll use the second equation with j equal 2 and x replaced by x minus a half. So I have minus phi of 2 x minus a half minus psi of 2 x minus a half. Okay. Now, it's time for a little bit of simplifying. Let's see where we're at. So, and also, because I want to distribute all this. So, of course, the 2 and 1/2 cancel out. So I have phi of 2x plus psi of 2x. And over here, I have phi of 2x again. Minus psi of 2x. So those cancel. And then I have, and then the others will add together. And then I have plus 1/2 phi of, I'll distribute 2x minus 1 plus 1/2 psi of 2x minus 1 minus 1/2 phi 2x minus 1 plus 1/2 psi 2x minus 1. Okay, now we have some cancellation. These guys, so that helps. Okay, so now let's combine whatever we have left. So I have 2 phi of 2x. And then these two add together, so I have plus psi of 2x minus 1. Okay. Now, so notice I started with functions that were sums of terms involving phi of 4x, 4x minus 1, 4x minus 2. Now, using these equations, I'm up at this scale, all involving 2x, 2x minus 1. And also not just the scaling function, also the wavelet, so the details coming from a wavelet. But I need to go further because this is in V1, which I can't have. I need to have only V0 and then any W I want. So this is in V1, this is in W1, which is okay. So I don't have to do anything more with that term. But for this term, I can use this again. In fact, I have phi of 2x written out right there. So I'm going to get the phi of x plus psi of x plus psi of 2x minus 1. So now I have terms in V0, W0, and W1. And now my decomposition is complete. So if I take a look at these terms, I have a scaling function. Oh, that's a really bad picture.
You get the idea.
Yeah, so that's my piece from V0. Then from W0, that is a wavelet. So notice it has a little more detail involved. And then here we have 2x minus 1. So that is a shift well, okay. So if I make this a little finer, but then in scale, but then shift it by 1/2. So make sure I get this right. So, okay, yeah. So this is my piece from W1. So each one contributes a little more detail than the last because you have a function varying over smaller intervals. Here, we're covering interval width 1, piecewise constant on intervals of width 1/2, and here's piecewise constant on intervals of width 1/4, and so on. So that's why that's the decomposition we want, that we're going to get a bunch of terms with these increasingly finer scales. Okay. So any questions about how I used those equations on the left to get this on the right? Now, so you can try this on whatever example you're given. But at this point, it still seems kind of ad hoc in a way, because you can see how you can just repeatedly apply these equations. But we want to be able to just have an algorithm, that's something you can just code up, to because you want to get these coefficients of these terms. Like in this case, the coefficients all happen to be 1. So that's a contrived textbook example. It sort of worked out that way. But you want to be able to get the coefficients of these terms directly from the coefficients of your original terms. This examples and these equations suggest how to do that, but now I want to actually write that out. Okay. Okay. All right. So what we do is, and this is something that really is not all that apparent from the example, but actually, yeah, it is just not obvious. So I want to highlight this before I continue. Notice that if you look at these two terms that came from the first two terms of the original, we had terms combine and we had terms cancel. Because of phi 2x showing in both, and then psi 2x showing up with opposite sides. And then for these terms, we got these, and again, we had phi of phi's and psi's either combining or canceling again. That's something that is no accident, because what happens is, here we have consecutive terms like 4x, 4x minus 1, and then over here, 4x minus 2, 4x minus 3. In any kind of situation like that, you're going to get terms of the same form. So here, both of these have phi of 2x. Here, both of these have phi of 2 times x minus a half. That always happens. So what that suggests is, if there's something to be gained by considering all the even numbered terms that have like 4x, 4x minus 2, etc., and also the odd number terms, that they have something in common. Okay. All right. So, to make this more general, so I'll write our original function in that form, looking at even and odd number terms separately. So we have a2k by 2jx minus 2k. All right, that's the even and then the odd. a 2k plus 1 phi 2jx minus 2k minus 1. All right. Now, and the reason I'm doing that is that now each of these terms are a certain form, and we can use the equations from before that I've just erased to figure out how to manipulate all these things. Because so now I can take this, so phi of 2jx minus 2k can be written as 1/2 phi 2 to the j minus 1x minus k, because if you think of this in terms, if I rewrite this as 2 factored out, 2 to j minus 1x minus k, this is playing a role of x from before, so that's why I have that here. And then the other term, same thing, except with the wavelet instead of scaling function. All right, and that's similar to what happened over here, where I wrote this as 4 times x minus 1/2, so now we have 2 times x minus 1/2. So you pull a 2 out of this, and that's what goes here. It's the same idea. All right. All right, so now similar idea with other odd number terms with an extra minus 1 in there. So, so similar idea where I just have same arguments to phi and psi, but as we saw before, we have a minus. Okay, so, whoops, come on. All right. Okay, so now I have, so what's happening is the even number terms are giving rise to, well, both even and odd terms are giving rise to these, in terms of this form, and in terms of this form. So what I can do now is, I can now rewrite fj as a sum, and the idea is, I now want to write this in terms of these functions that are now at a coarser scale, and also these terms that have introduced the detail terms, the wavelet terms. So I'm going to intentionally leave this blank for a bit. So I can have something multiplying phi 2 to j minus 1x minus k plus another coefficient expression times psi 2 to j minus 1x minus k. All right, and actually, all right, I have to squeeze in a summation. I don't absolutely have to squeeze in a summation because they're all part of some of the same index, but it'll help later. Okay. Now, what do I need to fill in here? I need to fill in whatever's multiplying these. Well, I have even coefficients contributing to this, odd coefficients contributing to this, and I have a 1/2. So I'll have a2k plus a2k plus 1 over 2 for that part. And then over here, same thing except with a minus. Okay. All right. So now I've managed to rewrite f, and what I've gained from all this is the original sum, because f itself is in Vj. Well, this sum is in Vj minus 1. And this is in Wj minus 1. So I've broken the Fj down into terms from at lower index scales. And the Wj minus 1 is something I want in my final decomposition, so now I can leave it alone. I can now focus on this and just keep going until I get all the way down to a sum of like a V0 and a W0, and then I'll have these other higher index W terms already there. So that's basically how the decomposition works. And so I have a theorem to that effect, that really it's basically this. So really it boils down to you're just combining the coefficients from your original to get the coefficients of a new one. So once you have these coefficients, you just feed this function back into here and keep going. So that's something that if you needed to, you don't have to for this class, but you could code it up in MATLAB.
Sounds like fun.
In fact, I don't know if this is in any of the homework problems because I've only assigned a few from this chapter so far. I need to look at the rest. It is possible to describe this whole process of going from the original coefficients to these all the way to the final stage as like a matrix vector multiplication. And that's why we actually have like a Haar wavelet transform. Just as a Fourier transform can be described as a matrix vector multiplication, so can this. Now that takes order n squared operations, but because of a nice structure here, how it's just averaging or taking differences of these coefficients, it could be accomplished in n log n operations. It can be sped up, just like the FFT. I won't get into the detail of that, but I just want to point out that something that has been worked out. Okay. So, questions about this process? All right. All right, so that is decomposition. Now, what about going the other way? And that's actually a similar process by the time you see the overall algorithm. Okay. So let's assume that but we have a decomposition. Maybe we've already done some processing on it, whether it's doing compression or devoicing. And now we want to get back to a form more like that. Okay. So, Reconstruction. That did not suddenly become a history class. Reconstruction. Okay. All right. So, all right. So the idea is, given f now in this form, so we have f naught plus w naught plus w1, and so on, all the way down to wj minus 1. So each of these are in their respective w spaces, and little f naught is in v naught. But the entire signal is in Vj, and it always is, no matter how it's written. We want to get it into this form, where it's the sum of coefficients at level j times the scaling functions also at level j. So, so here we have some coefficients in each of these terms. We want to get to these at different scales. How do we get to all these coefficients at one scale, the finest scale? Okay. Now, I need to write out what form these other terms have. So f naught, man, 4 is worse than ever. It's not going to survive a semester.
Yeah, but would you want a board that would survive a semester? It's just,
So people can read it.
Yeah. Chalkboards being necessary for things like education.
Yeah.
What luxuries.
And then each w has a linear combination of wavelets at, now here, but f naught is only the coarsest scale, but here we have all the different scales. Okay. So we're given our decomposition in this form. So each one of these terms, we have j plus 1 terms, and they have these respective forms. So now we just need to go from all of this to this right here. Okay. What we're going to use are similar equations to what we had before for a decomposition, just going in reverse. So I can write the scaling function as a sum of scaling functions at the next finest level. And again, this is easiest to see using graphs. Then I have something that's non-zero in the first half plus something that's non-zero only in the second half equals something that is non-zero on both halves. So that's literally the proof of this equation. And we have a similar one for the wavelet. So wavelet at x is the difference of these functions. Because if we took that minus that, so I'll negate it, gives a wavelet. So before, we had equations to go from a finer scale to a coarser scale. Now it's the other way around. So that's what how we're going to do this. That we're going to take f naught, which is currently expressed at the coarsest scale, and bring it down to the finest scale, or one at a time, and just keep going until the whole thing is at the finest scale. Okay. Now here I've written how to go from x to 2x, but just like I did with the decomposition, I can use this to navigate between any two scales just by making a substitution. Okay, so just rewriting his equations in a more general scale. So 2j minus 1x is psi 2 to the jx plus psi 2 jx minus 1. And psi, the same thing, is just a difference. Okay. Because notice before we had 2 to the jx on the left and 2 to the j minus 1x on the right. Now it's the opposite. Okay. So, what that means is, I can rewrite f0, which is originally in this form. Okay, so a, k, 0. I'm using a superscript to indicate which scale I'm currently at. So, from my decomposition, I have this, but now I can write it as a linear combination of, oh, I have a dang typo in my notes. Okay, hold on. So it's a different index. AL1, so I'm going down to the next finer scale, by 2x minus L. Now, the question is, how do I get these coefficients at level 1 from these coefficients at level 0? It turns out it's surprisingly easy. All I'm doing is I'm breaking this term that's non-zero on an interval of width 1 into two terms that are non-zero on an interval of width 1/2. And the coefficients just get distributed to those two halves. So A1 2k is equal to AK0. And then A2k plus 1 is equal to also AK0. So I'm just taking one coefficient and distributing it as is to two terms. So, seems kind of boring when you think about it. Now that's for the F0 part. But I could do the same thing with the W0 part, which is at the same scale. And there it gets slightly more interesting. So W0, which is originally given as from these coefficients, BK0 psi of x minus k, is now written as some BL1 psi of 2x minus L. And to get the coefficients in that case, so again, oh, wait a minute. No, not here. On phi. So I start with a wavelet, but I end with a scaling function. Because what we have here is B2K1 is BK0, and B2K plus 1 is is equal to minus bk0. And the reason for that is for a second or right half of a wavelet is the negation of a scaling function at finer resolution. That's like the next finer scale. So in other words, I'm saying that, well, actually, it's this equation right here. The wavelet is equal to the difference of scaling functions at the next finer scale, one shifted right next to the other. So that's why I'm copying coefficient for the left half, it's positive, negating it for the right half, it's negative. Okay. Okay. So now what I can do is I have F naught now in this form and W naught in this form. Notice they're both combinations of exactly the same functions. Scaling functions at 2x minus L. So I can add these coefficients together. So F naught plus W naught is now a sum of, okay, make sure I have this right. Okay, A L1 phi 2x minus L, where A2k1 is equal to AK0 plus BK0, and then A2k plus 1 is equal to AK0 minus BK0. So that's really how the reconstruction works. But I'm always adding on the accumulated function with the next level of detail, the next combination of wavelets, and this is how I get the coefficients of a combination. And so I showed you here how you tack on W naught to F naught, and now we have something that belongs to V1. So then I would add on W1 in the same fashion, combining the coefficients exactly the same way to get something in V2. And I keep going until I've used up all the terms in my decomposition, and the result is a combination of scaling functions at my finest scale, 2 to the jx, something in Vj, and then I'm done. So I've brought my signal back to the same form that I originally had it in. Okay. Okay. So what I can do now, and actually this works out pretty well, in spite of starting a class very late. Sorry about that. Basically conclude the discussion of reconstruction. So I'll just wrap up with a theorem that nicely summarizes all of this in a way that is more conducive to implementation. Okay. So again, you have this form to start with, and we have, this is my theorem. It describes reconstruction. All right, and we have, I'll just put everything in one place. So F naught is a sum AK0 phi x minus k in V naught, and then each W then f can be written in this form. I don't know how you guys can read this. I can barely read what I'm writing. AKJ phi 2jx minus k in bj, where to get the coefficients, A2KL is AKL plus BKL. Wait, something. Hold on. Okay, I need to confirm this book. Theorem. Okay. Oh, right. Okay. Typo in the notes. Okay. L minus 1 up here. Make this bigger. AK L minus 1 plus BK L minus 1. And then A2K plus 1 L is equal to AK L minus 1 minus BK L minus 1. Okay, so, and L goes from 1 up to J. So if J passes, you can get from here to here. So you're building up these coefficients starting at scale 1 and going, and you just, the idea is first you throw in coefficients from F0 and W0, then you're throwing in coefficients from that sum and then from W1, then from that sum and W2, and you just keep accumulating until you've used up all the W terms, and then your reconstruction is complete. So you're building it up from the coarsest scale and keep adding more and more detail until you have everything. Again, something that could be described or implemented like in an FFT-like fashion for greater efficiency. Questions about what happened here? I was just about what happened here as if it's a crime scene or something. Well, you always talk about like violence or something in math, which I'm not sure what that means, but yeah.
Well, that's the point. It has no meaning.
Okay. But in math, we got to define everything. Yeah. So there you go.
Well, but I think to be fair, asking what happened here, you're kind of hinting. Do you see what's going on?
Okay.
And that's a fair question.
Yep. Okay.
Unfair.
Well,
Unfortunately, too fair a question.
Well, it might be difficult to see what happened here, considering the board, but. But that's what the notes are for, I guess.
Yeah.
Also, you can't see very well what's happening in the book because the PDF is so awful.
But the PDF is a whole lot better than spending $100.
Okay.
I'm not going to knock.
Yeah.
I'm not going to knock a free book here.
Yep.
It could be the greatest piece of garbage in the world.
Well, okay.
I like my hundreds. They come too hard by.
So the funny thing is, because the idea is between today and Monday to cover sections 4.3 and 4.4, which I've mostly done. Well, I guess I have a little bit left of 4.3 for next time. Because 4.4 basically is a summary of all of this, but I've kind of done that. But again, there's sort of an opportunity for homework questions, I suppose. But yeah, we'll wrap up this chapter on Monday, and then we'll get into the final chapter, chapter 5, on multi-resolution analysis. So, okay, well, there you have it.